The greatest pleasure this morning to welcome Thomas Everett from Mercury Bay Area School. We've been in touch with Thomas quite a bit over the year, just finally was able to nail him down for this session. So please join me in welcoming Thomas Everett, who's going to talk to us about connecting statistics with Earth and space science.
Thank you very much. So what I'll do is I'll start sharing my screen and we'll see how we start from there. Let's see, where is my screen going? There, share, and I need to start presentation, slideshow. So can anybody see that? It's all on?
Yes.
Yeah, fantastic. Good. So briefly introduction. So my name is Thomas Everett. As you can hear from my accent, I wasn't born here. I was born in Germany. Well back in the day now, and I got a degree in physics from Germany, also well back in the day. Spent 30 years in the IT industry, started a company after my physics degree back in the early 80s, and then while I stay in America for 5 years, working there. Finally in 95, sailed across the Pacific on a small little boat that I had myself at the time. And came via the atomic protester at Mururoa in touch with a wonderful Kiwi whom I married to since then. And we settled in Coromandel Town, and a bit later in my life, when I was sort of sick of looking into square screens for my profession, I got a teaching degree in 2010 at the University of Waikato, and have been teaching since then, mostly at Mercury Bay Area School in Whitianga. And over the last few years teaching there, I developed this course that I'm talking to you about today, combining Earth and space science and statistics. Since the beginning of last year, I've finished teaching at Mercury Bay Area School, and I'm back at university undertaking a PhD in education, working on climate change education. So that's me, and so I'll start out with my slides. I tend to begin my slides with a postcard from planet Earth, just to sort of set the tune a little bit. It looks like a fever curve, of course. As fever curves are, there are symptoms. In this case, the disease that creates this fever is cultural. And I think that as teachers and working at schools and education institutions, working with this cultural disease, quote unquote, and again in a wider context, will become probably very much our mahi, because if you want to survive that fever curve, we have to change what we do. And of course, education is the best place to make a good start on changing the culture that created that fever curve and doing something different. And I think statistics has a big role to play in educating students and the people generally into understanding Earth systems and dynamics within that. So I think talking to the converted probably here, that statistics is hugely important. So this is the traditional view that I think we all sort of know is how education at schools and also universities to some degree has been progressing, where we have these silos of mathematics, physics, chemistry, biology, and all the other subjects. And very often at high schools particularly, you're finding yourselves in one of these faculty silos, and it's very often not even really much known what the other silo is next to you is actually doing, what the students are engaged with there. And that's a bit of a sad state of affairs, because the world is not siloed, everything is connected, and we're learning more and more about the degree of connectedness among everything. And I think my personal feeling is we need to work much more closely together across those silos. So I started with a little cartoon. When I went to teacher college, this was the view that I had sort of in my mind. This is how teaching would look like. There's this wonderful New Zealand curriculum here that we all aspire to, and it's all worldly and leads the students. They're sitting in glee here on the carriage, the teachers, giving the course, of course, and we're working towards learning about the world. And there's a little guy sort of running behind. It's the NZQA guy, and he kind of stems things along the way if they're worthy stemping, and that's about the role that this person there has. But of course, as you all know, then once I got my first job, it looked different. This is the cartoon image of having your first job, walking in and being told that the curriculum is sitting sort of up there on the shelf with a bit of dust on it, and all these folders full of achievement standards, and it's all about that. It's all about the man with the stem. He is dictating what we're all doing every term and every year, pretty much so. At least that's how I perceived it, and so I turned this into a little cartoon. And there's always cartoons that are kind of funny. They also contain a bit of truth, and I think this cartoon embodies some of the embodied or in practice way that teaching at high schools is perceived or has been perceived. And so I think this needs to change back to what it was before. But anyway, so this is my concern that schools have been very much educating hoop jumpers that learned to pass exams rather than learning in a contextualized and connected way. And so what I was going to do at Mercury Area School was trying to work not in this sort of picture, but to do something different. So one of my main concerns always has been the bifurcation of the mathematics, the embodied mathematics teaching at our high schools. We have this statistics stream generally and a calculus stream generally, and it sort of bifurcates the whole student body into these two streams. And point in case is my daughter, she went into the calculus stream. She actually turned out to be dux at our school at the end, which was great. Of course, her last time that she would have integrated anything was probably at the last year 13 exam. She then went to university and studied ecology, marine ecology. And in her first year there, she would have needed statistics. But she didn't have that at school. She had calculus at school because most of the quote unquote really good math students end up in the calculus stream, and it's mostly those who go to university, and the majority of those will find that they actually would have benefited from statistics later on. And then we have these other silos here, of course, of those subject areas. And so that's a concern. So this is why I think this is the way it could look. And this is partly what I have done, and I'll show you in a minute how I've done it. So being a physicist myself, I have always really looked at the fact that physics and calculus had been separated as a real misfortune because the physics curriculum at our high schools in textbooks and everything else has taken calculus back out of physics, which is a crime. When I went to high school in Germany at year 11, we started parallel to a physics class. We had baby calculus in the math class. So we were learning year 11 physics with the little d's rather than the big deltas, and we're seamlessly learning how to differentiate and integrate for 3 years until we left high school. And the math stream had the physics stream always to play ball with, and we did vector calculus at the end of year 13 seamlessly. It was easily possible. So we've done 3 years of calculus from baby steps to vector calculus at high school. Statistics, I believe, has a lot to do with many other subject areas, from economics, PE and health, earth and space science, which I'll talk about, biology, social studies, education for sustainability. All those subjects, and probably others as well, could interlink actually really well with statistics if those subjects were taught in context. And so I'll talk about that a bit more. In my case in particular, what I was offering to our school was to have a combined multi-year course of earth and space science and statistics, which would allow the calculus students to choose earth and space science and stats as one of their science subjects, which then at the end of it allowed them to leave high school with a level 3 statistics outcome, plus one of the sciences, and then they would choose one of the other sciences as well if they wanted to. And that gave them this sort of more richer outcome. So I'll show you what I've done. One more motivational slide here. That's, of course, the real world is not siloed, and even the New Zealand curriculum actually sort of speaks towards not having education siloed. And in real life, you know, you have to, at the end of the day, be able to combine different skills in your work. So that's what I've done in earth and space science and statistics in Mercury Bay Area School. I created a 2-year progression course for year 12 and year 13 students who were together in the same course, in the same class. And the class had the class had an A and B year. I'll talk about it more in a minute. And students could enter at the A year or the B year. There was no particular rhythm between which one was first. And so the students spent 2 years in my course. All the work was at level 3, because the level 2 statistics standards at NZQA I find a little bit boring. And students at year 12 were quite capable to do the level 3 work under the education that we gave them. So introduce where we are. So here we are. That's our neighborhood, Mercury Bay Area School. And we're only 5 minutes away from the estuarine environment of our wonderful estuary here. And we have a whole bunch of sort of tidal rivers in our neighborhood. So my Earth and Space Science course centered on the oceans and on the estuarine environment, really, and use the environment that we have as a spout for data for statistical investigations and Earth and Space Science investigations. Here a bit of a picture of how this looks when we go out to our environment. And I gave the students a wide range of choices of what they wanted to investigate. What we normally did was on our first couple of lessons in the year, I took the students out and asked them to bring their cell phone as a camera, bring a notepad, and we just sat around the estuarine border of the Whittinger estuary, and I asked the students in small groups of 2 or 3 to get together and wander around and observe what they'd see and whether there was anything there that sort of seemed to be interesting. Why is it this way or not that way? And so students here, for example, on the left, they started to wonder why there are so many crab holes in the ground in one area and not in the other. And I'll talk about that in a minute later. Other students wondered about whether or not the thickness and the softness of the mud played a role as to where would the mangroves settle, the young mangroves. I did a study on that. And I constructed a floating data logger, which would log, and I have a picture of this here, which would log a number of parameters of the water in which was floating, salinity, pH, dissolved oxygen, turbidity, temperature, and together with a cell phone, we could also capture latitude and longitude, and it would log this data every 10 minutes on an SD card, and that was a wonderful data spout for students to investigate parameters in our estuarine rivers, see tidal cycling happening, and so forth. And I'm a friend of Jake Wills, the maker of NZ Grapher, whom you probably all know. I mean, you definitely know the software. And we cooperated a little bit on making his software able to encode arbitrary time series to arbitrary intervals, which are needed for tidal rhythms, et cetera, and a bunch of other things. So it was a cool stuff to do. So this is what my course looked like that I designed. So it was an Earth and Space Science centric course with statistics built in. So here's my year A, and the year A was sort of an ocean system centric year. The students would write an essay in Earth and Space Science on tidal forces, on astronomy, tidal forces, and the life cycle on the icy moons. It's interesting for astronomy that we're now looking for possibly signs of life on the moons around the large planets in the solar system. And it's interesting that the tidal forces on those moons may provide the energy for those life forces there. We also every year did a practical investigation in our estuarine environment. I'll talk about that more in a minute, where students would investigate themselves and bring data back. In the first year, we focused on time series and bivariate statistics. And those 2 internals were based normally on the data generated from my data logger. And then followed an external in Earth and Space Science, and also an external in probability distributions and mathematics. That would run every year, by the way. Not every student would enter this exam in every year, but they would do it once in their 2-year course with me. And in the second year, we focused a bit more on atmospheric systems. The students would generally write an essay on socio-scientific issues of climate change. We would then again use inferential statistics, and I'll talk about that more in a minute too, on sampling that we did in the estuarine environment. We did lab experiments based on climate change ideas, and then an external again on Earth processes in the atmosphere.
Thomas,
Yep.
Can I just jump in? There's a question about how does it work to enter into the A or B year
Okay, yeah, good question. So there's no reason that you had to be in the A or B year before the other. Students could enter in any of those years. It wasn't like you must have had A year to have B year. The years where you could enter in any of those years. We always started the year with a discussion on nature of science and writing science reports. I would support the students to use Zotero as a reference tool, for example, for their referencing, for collecting literature, and students who had already been with me 1 year would assist the students who would enter in the next year new. We grouped them differently, and so there was no reason why you had to be entering in a particular year. So we had always a mixture of year 12 and year 13 students together in the class, which was partially because our school is too small to support 2 separate classes of this nature, and but also it worked really well. So this is what the students then did. I asked them to not provide individual assessments, but to provide an annual report which had a continuity to it. So it was an annual report which allowed me to read it holistically, and where they would have an introductory chapter where they talk about the astronaut environment, and I could use that as assessing for these stats assessments coming off the data, because there was the reasoning as to why we would do these investigations. There was the background science, and it would flow into all their further assessments, which formed different chapters in their booklet. And in the end, they had a summary and they had references in there. And it looked like a really nice booklet. Some students over the year collected about 40 to 60 pages worth of writing. They were really proud of it. And in our English department, we had a course called English for Scientists, which was really cool. And so the students could use some of this work as evidence for their course as well, because they did really good writing and really extensive writing, and they would normally provide a oral presentation of this work in their English for Scientists class, which tied it in really well for them as well on that course. So the first year and the second year, again, a booklet with summaries and references in the end, and it prepared them for university work really with what they were doing. Again, while this is little comics, I can jump over this. Yeah, this is the comment here again, that they used the writing that they did also in parallel with their English for Scientists course at our school. A course that I recommend to do for schools who have the ability to have different tranches in English, make a course English for Scientists, where students read a lot of scientific literature and learn the particular styles of that writing, learn how to disseminate sources and so forth. It's quite a good course.
Thomas, there's a few more questions that have popped up. Oh, and it looks like you might be going to answer one. So one of them was about UE, so I might leave that because that. How does the ability range of students entering this program at what is the ability range of students entering this program at year 12, both in terms of literacy and numeracy? And how do you incorporate the level 3 probability and distributions into this course, or are they taught separately?
Yes. Okay, we're happy to talk about this. I'll come to some of those points in my presentation anyway. Right. Maybe let's start with the UE here. So normally if students spend 2 years in my course, they would end up with up to 20 level 3 credits in Earth and Space Science and up to 20 in statistics, depending if they all did the external that was offered and did all the internals. Some students left it at 14 credit, at 16 credits and so forth. However, some students got the whole number of credits that we had, which meant also that after 2 years in my course, those students ended up having 2 independent UE subjects, which was another benefit. And they also had quite a number of reading writing credits from this one course for the UE as well. Student ability, yeah, I had quite a mix of students. I had some students that were highly capable and left school with scholarships. One of my students left school with scholarship and then went to Dunedin and was immediately their best of class of 250 in her class of marine ecology. That wasn't my daughter, but somebody else. And my daughter was at our school before I did this course anyway. Others came into the course. We always had some students who selected Earth and Space Science because they found that biology, physics and chemistry was too difficult for them. We had some of those students. And some of the students ended up having only a few credits in my course as well, because they were just not of the caliber that they would write a lot. Yet they still enjoyed being in the course. They enjoyed being part of the practical investigations. For example, I had one team of 2 boys that went through my course, and I showed a little bit of their work later on. And one of them wanted to go to the army, become an officer, and due to my course, he was able to actually get level 3. He wouldn't have got level 3. He got most of the assessments at Earth and Space, Science and Stats at achieved level, but he made it, and is now an officer at the army. He had a friend who worked with him. The friend had virtually no credits anywhere at school, but he enjoyed being in the school. He learned a lot, didn't submit anything for assessment in the end, but he had a good time. Those guys worked together, and he really enjoyed being there. So it's not always about assessments and achievements for all students. It's quite often the journey that counts. And so I can say that not every student achieved at the high level that we want, and that's just the normal outcome that you get at schools. And some students had achieved outcomes, some students had selected assessments that they submitted and completed. Some students had just enough to have this course be a complement for the other courses to get level 3 at the rate that they wanted. So it was a mix of students as you would normally get. Good, we're from here. So I show a little bit what happened. So this data logger that I built delivers a CSV file of readings for the conductivity, salinity, dissolved oxygen, pH, something about turbidity, temperature, battery voltage, and so forth. Turbidity, by the way, also gave us a signal of the amount of sunlight that was there at the time. And then together with a cell phone combined latitude, longitude. So what can we do with that? We can chuck those data onto a beautiful website that you should check out if you haven't seen it yet. It's called gpsvisualizer.com. You chuck the table there and it draws you a map as to where you have been. This map was created by dragging the data logger behind a dinghy up a tidal river. Students enjoyed that very much as a field investigation. And so we can plot the changes of this water parameters. In this case, I think it's salinity, and plot it along the river. And students could then, for example, make a bivariate analysis as to how far am I along this trajectory from the river mouth where the ocean comes in towards the end. It could be a bivariate, for example, right? Or they can just comment in the Earth Space Science investigation about the different habitats and the different parts of this estuarine environment, and how could those parameters of the water that they observe maybe be an influence for the species living there, etc., and so forth. Bivariate data come out of this quite easily. You can see here one output from one of the students' work who wondered about the relationship between the salinity and the pH at the water levels we saw there. This was from a location where the data logger spent 5 or 6 days at one location and recorded tidal cycling. And we could then see that the pH level of the water also changed together with salinity with the tidal cycling, which was interesting because of the fact that the ocean water has a higher pH level than the fresh water when it comes down the river. Scientifically quite reasonably to be argued. And then, of course, time series come out of those. So the data logger spends maybe 8 or 10 days or 7 days at one location. The timestamps are located for every of these measurements every 10 minutes. And thanks to my software work with Jake, we now have an NZ grapher, the ability to encode that time signal into a time series type column. And it's your choice what your period will be. So the period could be the daily 24-hour period, or the period could be the 12.4166 hours tidal cycle, which was really interesting because students could observe whether or not, for example, the dissolved oxygen cycles with the tides, or does it cycle with the daily day and night rhythm. And we found out that in most of our rivers, the dissolved oxygen actually cycled with the sunlight, which makes sense because it's the sunlight that creates photosynthetically oxygen in the water column, and so at night the oxygen level drop and at days they rise, and we could observe all this. And so we got the time series coming out of this very same data. So it could be one investigation, one river, see how different relationships happen between different of these parameters, and what's the tidal cycling doing to the data, what's the daily cycling doing to the data, and the students are very interested and could eloquently then write an assessment out of it that combined Earth and space science and those two into one booklet, for example. The other one was sampling, for example, in the environment. Here's an example of some pictures of cockle shell sampling. Cockle shells are a very nice task for sampling from a population that you don't see. So the idea of having to take a sample is obvious. It's also obvious that you have choices to make as to how you sample and how you might randomize your sampling process, and why that's important. And why it's important not just to pick up some nice big shells on the surface, but to actually systematically randomly sample. It's also very cool if you have a class large enough that you have several groups of 2 or 3 students who sample together, and then you compare their different samples and look at the sampling distribution together in the class. And the students can then actually use their data and use each group's data to then, in their assessment, even write about the practically seen sampling distribution and how that fits together, and sample sizes and so forth. And so then what we did was we brought the shells home that we sampled, washed them carefully, measured the width, the length, and weighed the shells as well. So we had the weight, the thickness, the width, the length. We had some categories. We had year and the group who did the sampling. And we had a category which is how far from the shore the sampling was taken. The class normally sampled at 3 different locations. One was 15 meters away from the high tide line, the other was 32 meters away, and then the last one was 64 meters away from the high tide line. And so they could do a number of investigations, for example, looking at whether or not the median parameter of the shell was different depending on to how far from the high tide line you'd sample. And given the fact that we had a baseline in 2017, they could then compare shells between the different years as well. There's a number of different outcomes they could aim for. And I'll talk a little bit more about the interesting outcome we saw between 2017 and 19, and sort of is hinted here a little bit already in that small graph. So that was the sampling we did for inferential statistical inquiries. And some of the students did different sampling for different things for inferential statistics. Lab experiments, so we did statistical experiments, so what I found was, can you see this? Yeah, I found that in doctors' practices, when you go to have a blood sample taken, they have these styrofoam boxes, and the styrofoam boxes have a lid, and the lid, this is the lid of those, and there are 100 blood samples in those lids. And so the doctors will throw this away, so you can pick up a dozen of those or 100 of those at your local doctor's practice, and you're looking at 100 individual wells that are like a centimeter deep. And that's fantastic because you can use microgreens, for example, cress seeds, and the students can then randomly select 100 of those seeds into the plate. Or if they don't need 100 samples, they can make a red line in the middle, and they have their control and their treatment on different sides of the same plate. They're also quite handy to store. You can store all class set 1 in your classroom somewhere at the same locations, not different from each other. And so we use them quite extensively at our school, also in the biology classes. And so we have actually this particular assessment is done by the bio teacher in the bio class, together with me doing the stats work, and also in the Earth and Space Science class, also for various experiments that we did. And so, yeah, you got your experimental stats outcome there. The students then also take another random sample of actually plants from their 50 or 100 specimens to actually then measure their individual length and so forth. So that's the data generation for the experimental setup. And it's quite nice, and it fits in with the whole topic of climate change, because salt intrusion in in growing environments for plants, for example, is a big problem. It's a big problem because of rising sea levels in one point, and also a big problem for irrigation in very dry areas where people irrigate fields over and over and over again in areas where normally there's not enough rainfall to wash the salt away that accumulates when you irrigate and evaporate, irrigate, evaporate. And so large parts of the world are now becoming more and more saline, which actually is going to be a really massive problem for feeding the world population, a problem that's going to haunt us, I think, in the years to come. Anyway, a little bit on cockle shells. So when we surveyed our cockle shells, I made contact with the University of Waikato. There's Dr. Conrad Pildich. He is a cockle shell specialist. And we told him that we had seen, maybe I'll fast forward briefly, yeah, we had seen this at our school. This was just a brief overview of our data from sampling in 2017, the top row, and 2019, the bottom row. And these are the median or the width of the shell, the largest diameter of the shell. And you can see this dramatic change between the 2 years in the population parameters of our cockle shells. Dramatic. So I called up Conrad Pildich, said, look, we've seen this massive decline. And he said, wow, that's amazing, because we have seen a very similar decline in 2009 at Lee Marine Reserve, where they are sampling every year with their students. So I'll go back to Lee. So this is what they saw at Lee, right? So here is the annual sampling they do, and that's the density, and that's the length, the size of the shell. So that's the size parameter that we sampled, and that's their density. And look what happened in 2009. Now, this is a photo taken in 2009 when they took their sample. That's taken on the 13th of February, 2009. Now, mark that day, 13th of February, 2009, and you can actually see that some of these cockle shells that are opened up here on those massive shell beds, some of them still have the meat inside. So they just died. They just died. And so I said, well, that's amazing. And I went to a database from NEVA that I'll talk about in a minute more, because that's a nice data spot for stats teachers, database called clifflow, where you can download temperature data and weather data, meteorological data from NEVA. So I did that, and I time seried the temperature data from the Lee Marine Reserve's weather station that's been running since 1967 continuously by NEVA. And so look what happened in 2009. Boom. And then I did a histogram. This sort of work, by the way, was part of my probability teaching, and the question was raised before, and I'll come to that. So here is the histogram of the maximum February daily temperatures between the first decade in the data set and the last decade in the data set. And so the difference is obvious, and particularly though the high and the tail end, right? The tail end is particularly interesting. And a general comment as a climate scientist, a general comment, when we talk about temperature change, average temperature change of the globe, when we say the globe is warmed by 1.2, 1.5 degrees on average, that's talking about the median or the mean of the temperature shifting. Now, that may not be so significant. Like if you have the median temperature go from 23 point something, I think it's 22.8 is the median here, to 25.85, that sounds like, well, that's already a lot, but it's not so bad, right? This is the bad thing. Whenever you shift the median, you're shifting the tail end, right? And in the dramatic and catastrophic impacts of global warming, of climate change, this is where it hits. Because there are many environments where you suddenly breach threshold temperatures. Like if you have environments that can withstand a day or two at 28 to 29, but they can't withstand that amount of time spent there, right? So we have entire biotopes tipping, dying, because of the fact that they can no longer withstand the magnitude of the effect you get on the tail end of your distribution. And that was really important for my students to actually understand that part of it. The probability of very hot events has dramatically changed, and the probability of cold events has also dramatically changed. And some species need a couple of days of frost, for example, when it's not frost in February, but if you do the same thing for for the winter month, you see the same distribution kind of change, and you will see that you're missing the frost days. So if you need frost days in certain plants, I think cherries and other ones might need a day of frost to trigger their cycling. You don't have this anymore, you lose the species, right? So let's look a bit more carefully at the year 2009. So I took the daily temperatures and plotted them, and this is the day number, the number of the day. So 0 is the 1st of January, right? And so here is the 11th and 12th of February, the day before the photo was taken by the university. And then I went like, well, what else would happen at that day? What's the chance that on that day, the tide was low on the early afternoon? And so it turns out that it was. The tide was low in the early afternoon on that day, and also on that day, but not on that day. So these two here had early afternoon low tides, but from the photo, it's already clear that this here killed the cockle shell beds, because you had this coincidence of having early afternoon low tide when that heat event happened. And then when you teach the students probability, you can go like, well, what's the chance of that happening? You know, how often do we have an early afternoon low tide? Well, that's pretty easy to determine with tidal cycles. And, you know, what's the probability of having those events? Well, you know, what's the chance that we have every second or third year such an event happening? And it becomes quite probable, you know, and so the more often you have those high temperature events, the more often you'll hit these events that kill your cockle shell bed and kill all the big ones. And what happens is the big ones in the cockle shells segregate to the top of the shell bed, and the small ones are further down and protected. And so it's the big ones that die, that pop open, and it's the big ones, however, that are fecund, that are seeding the beds. And so anyway, so for my students, it was really interesting to engage with all this and to be a detective and say, let's be a detective and work out what was the day when those cockle shells died? Well, I think we can pinpoint the day and the hour when that happened. And we then dug out, or I dug out a paper for the students from 1971, where a researcher at the university in England somewhere cooked or heated up shells, in astral environment shells, until they died slowly. And I think most of those temperatures were sort of in the 28s to 30s, which were the threshold temperatures which killed those shells. Anyhow, interesting stuff. So back to this. In our Investron environment here, we then looked also in temperature data from our neighborhood, and there is a network of weather stations, of private weather stations, which is called the Wunderground, where many of the sort of stations that are owned privately, like our school has one that I got up for the school, and you can go there and find hundreds and hundreds of weather stations in New Zealand that post data to the internet on the Wunderground. And so we found about 5 in our neighborhood here, and they all seem to have a heat event. I'm not sure how true that was. 36 degrees and pretty young, that sounds a bit much, but there was certainly a heat event here and here in the year 2018. And this one also had a midday low tide for the 12th of February. So in that particular year, so we think that may have affected our cockle shells between the 2 years that we sampled. Anyway, let me come to something else. Let me come now to the real life of doing all this fantastic work and then being hit with external moderation. And so here the story becomes interesting, and interesting in a number of ways. So let me explain that. When I became a teacher in 2012, I went as a beginning teacher. I went to a workshop. It was a science moderation workshop at Natia. And unfortunately, I forget who the presenter was, but the presenter was the chief science moderator for NZQA. He presented at Natia to us, and he stood on the stage there, and he took this achievement standard as a science standard 1.6. The very same one exists still today. It's about the use of fossil fuels, and in the Jeff, underneath the boxes A, B, C here, in the explanatory notes underneath there, there are a couple of points, and one of them is the students has to show knowledge of the boiling points of benzene and other such fossil fuels. That's part of what they have to show. It's still in the standard today, by the way. And so he stood on the stage and he took the standard and he ripped it literally in front of us, ripped the piece of paper here and threw away all the stuff underneath and threw it in the bin and said, I want you to look at these three boxes holistically, and that's the chief science moderator. I want you to look at these three boxes. And I want you to think what you could do with the students as an achievement assessment work that would speak holistically to those boxes. And if you bring me students' work that has done that, I'll be very, very happy. And he cited one work of a student in a class that used a standard where the uncle of the student had a forge and he was making his own knives. And the uncle used different coals as fossil fuels to achieve different results in the forge. And the student investigated that, and it was a really good report, really well done. The teacher gave it an excellence. But on first external moderation, the first external moderator said, no, it's not achieved because the student didn't show evidence of knowing the boiling point of benzene. Of course, it's irrelevant for that particular work, right? So it boiled up to this chief science moderator, and he reinstated the excellence grade, saying this was fantastic work, and he, in front of us, ripped all the stuff off, you know. So I have ever thereafter lived my life teaching by this. I have always basically looked at what was there and then go like, well, yeah, but, you know, I really want to have my students to have a good learning outcome, and I rather fight the external moderation than curtail my students' learning, which got me into trouble. However, my troubles have been always ending up in success in the end. So in the first year, my moderation was called out by the Earth and Space Science moderator, who concluded that sampling in the asteroid environment with biological specimens was not Earth and space science, that was biology. And therefore, all my students had not achieved in Earth and space science. So I wrote to some people that I know, like professors for ecology and so forth at University of Waikato and others. My friend is also James Renwick from University of Wellington. And so I said to them, look, you know, do you think asteroid science is part of Earth and space science? Yes, very much so, they all said. That's part of what we do at the university. It's definitely part of our Earth and space science is studying asteroid environments, hugely important for climate and everything else. So I got a few letters together and wrote back in and appealed, and arrived was an apology from NZQA saying, we deeply apologize. We're very sorry about the first external moderation. Yes, Earth and space science is definitely part of, or asteroid science, definitely part of Earth and space science and so forth. And our principal nominee danced around the staff room with the letter in hand and said, this is the very first time in my 40-year career that I got an apology from NZQA, and he pasted it on his office wall. And anyway, it was kind of cool. And then in my last year of teaching at Mercury Bay Area School, before I started my work at the university now, my statistics papers were called in for external moderation, where my students had sampled the cockle shells and did an inferential stats paper on that. And the external moderation said, oh no, that's not achieved, because it says in the explanatory notes down there, the students have to be given a data set. And those students made their own data set with their own sampled data. That's not appropriate. So I went like, well, that's weird. So I appealed, and the appeal again came back. No, definitely the students cannot sample. Actually, literally, it was said the students are not allowed to sample. They have to be given a data set. So yeah, anyway, I said, okay, well, you know, my student grades stood. They weren't affected, but I wasn't happy, and I commented a few places, including the Facebook page of maybe you guys, on the fact that that my standard had been not achieved because students sampled their own data. And then earlier this year, I got a call from Neil from NZQA saying, "Oh, yeah, well, actually, apology, and actually we looked at your data again. Actually, it's kind of nice. Can you send us your assessment standards as an exemplar for our website?" And I'm like, "Oh, yeah, great, I'll help you." I really love working with NZQA to show cross-curricular working, and so we co-constructed with the help of the chief statistics moderator, I believe, from NZQA, or one of them anyway, co-constructed an assessment task that fits the bill. The students still have to be sort of given some data, I think, but they can contribute by sampling to the data. And so what we made is we made a data set, and I'm happy to share my data sets where, for example, if a school wants to sample near their estuary, they can use my data set as part of what they're given, and then they can contribute their own data to it and compare the two sample size, for example, etc. And the other thing you can do it, of course, is what I did was I used all the students' samples from the different groups, and I made a compound table out of all of them and actually gave my students the data table for their assessment. But some people still initially believed that students who had contributed to the sample would make it not accessible, this whole thing. Anyway, so success. So I would encourage people to think holistically about the work you do and argue with external moderation. It's a cool process, and people are really keen to hear from you, and it's a good process. It's good for all of us that we challenge the external moderators. It's good work, good money for them, good money for us. Cool. So what I might do is I might have a little break in my choreo at the moment, because I have some more slides that would give some hints to people who do not sit with their schools near an astron environment, and who cannot probably leave the school grounds very much, because I have some ideas how to get lots of data otherwise. But maybe a brief break and some questions, and I'll show what else I got. Just a couple more slides really on what else to do. So I'm not looking at the chat, unfortunately, because otherwise I'll be overwhelmed. But so maybe.
Yeah. So a couple of things that came up, Thomas. One of them was about opportunities to interact with NIWA or environment BOP. And I think in some ways you answered that by the reference you did to the Lee data and things like that. So hopefully that.
And particularly exactly to this, I have another slide with some interesting stuff for you guys. Yeah, from NIWA. Yeah. And
the other question was approximately how many students are in your A year and B year. But I suspect the question is how many students are in your class at any given time.
Yes, so because our school is comparatively small, our high school end of Mercury Bay Area School is about 400 students from year 11 to year 13. And traditionally, students still would select mostly biophysics or chemistry. So I had normally, in my best times, I had about 15 students in the class. And I had also a year where I had only 8. So it varied. It was sort of at the bottom end of viability, but it was definitely, even with 8 students, a viable class. Yeah, because we sometimes do only have 8 students in year 13 physics, for example, or even less. I think this year the teacher had only had 5 students in year 13 physics, so that happens, Yeah.
There's been there's been many comments along the lines of people wanting to get a data probe now. Amazing, interesting. The fact that teachers are genuinely investigating and drawing conclusions ourselves, and through that, sort of that idea that they're in capture the energy and inspiration for their students. So there's lots of really good feedback on that. I want to make a comment, which I think is pertinent to your moderation. When a standard, and this is my interpretation from being one of the writers of the standard, the reason the standard was written as given was we didn't want everyone to have to collect. The information we had back then was never that you couldn't collect. But moderation has their own way of looking at things. And I'm really glad you had a successful outcome with that. That shows promise for us looking into the future, that we shouldn't be restricted, as you say, by not allowing kids to be involved in the process of gathering the data. That's more about saying, well, you don't have to, but wouldn't it be nice if you wanted to? We've got about probably 5 minutes max. There is another question: how do you incorporate external learning prep into your course? And then I might let you just finish up.
Yeah, I would like to briefly show a couple of slides because people would like to get data for themselves, right? And so my data probe that I made, I'm happy to share my plans and everything for it, but I would caution that I got a 30-year experience in IT and in electronics. I've built whole computer systems at university back in the day. So it needs a bit of skill to do this thing, but there are other ways of doing it, and I'm happy to engage maybe with sharing some stuff later as well via our ongoing dialogue perhaps. But just briefly on a couple of data spouts. So one data spout is for sea level data in particular, and it's for time series, is a website called psmls.org, where you can get sea level data from some stations for a long history. This is the Sydney Harbour tidal gauge at Fort Denison. And you can see the sea level development here since the early 20th century up till now. Very interesting stuff. And people can explore this for themselves. But the one I want to talk about is this one here, NIVA. So NIVA has a database open to the public. You can make yourself an account on it for free, called clifflow.niva.co.nz. That has data from all over New Zealand, from weather stations that automatically report into their database, I believe. And you can download all sorts of things. For example, temperature, rainfall, winds, all sorts of stuff you can download there. The user interface of the database is not easy to navigate, unfortunately. But I'm at the moment trying to talk to NIVA about myself and Jack Wills from NZ Grapher making an overlay for this database, a student-teacher focused overlay of this database that allows us to download data in a useful way quickly from it, but that may be a way off. But you can still get data from it, and I can maybe in a different workshop show people how it's actually done. It's unfortunately not easy to get the data that you get from there into a way that you can use it in NZ Grapher, but it's possible. So here are some examples by variate, the temperature to the dew point, for example, is an interesting one. Or inferential stats as well, comparing samples between different years and so forth, doing sampling out of this table that you can get there would lead to this. So you can get your three main internals basically out of this database if you so wish, if you set it up properly. What else did I have? Oh yeah, and probability. So I also inspired Jake to put this modeling component into NZ Grapher. With what I wanted to do was I wanted to teach students the probability stats based on some of the data we made ourselves and data from NIVA and so forth. And so you can model your distributions now on data in NZ Grapher yourself. You need to explore it there, but you probably have already seen it. And that's kind of nice then to use those data and type it in your stats calculator, and you can work out things there. And you have different distributions. This is a normal one. You can try different distributions and get the data back from there. Yeah, so maybe there was one more particular question about something. Pip, I forgot now what you said.
There's so much scrolling in saying thank you about it being inspirational and everything. There was one question about how many hours per week was this course, and how do you incorporate the external learning prep into the course? Yeah.
Okay, so the course was our lessons at Mercury Bay Area School are 70 or 90-minute lessons. 90-minute lessons normally, and we had 3 90-minute lessons per week. So that makes it, in other schools, it will be 5 lessons or something a week, depending on your length of it. And we sometimes, when we are sampling, we took half a day, or we went over lunch break, and we sometimes would borrow a day for the students to be out in the field as you would. The external preparation, so we normally did all the data gathering in term 1 and 2. We did finishing off the internals in the second half of term 2, beginning of term 3, and then left the second half of term 3 and a bit of term 4 you got for teaching the context for the external exams, the probability and the external exam for ESS. Pretty much as you normally would do in a course anyway. And the Earth and Space Science was partially interwoven with teaching anyway, because some of the topics that are taught about, that are assessed in the externals for Earth and Space Science come about as we talk about the science that is involved in looking in the astral environments or looking at the ocean environment, atmospheric environments and so forth. So that's interwoven there. Yeah.
Fantastic. Look, Thomas, I've been enthralled through the whole process of the story and the journey you've taken us on today. And I think that's why we teach statistics, is because we want to know about things that are happening in the world. And I think you really put that out in front.